Hi everyone, my name is Khan. I'm a PhD student at IBM Research Zurich and ETH, and today I'm going to talk about practical lattice-based zero-knowledge proofs for integer relations. So this is joint work with Vadim Lyubashevsky and Gregor Seiler. Okay, so let's start with some motivation. So why are proofs of integer relations like addition or multiplication useful in real world? Let's see. Okay, so the first example is pretty common, is let's say suppose we have a payment system where people send money, make payments and so on. Then it would be essential to prove that we have enough money in our bank account to actually make such a payment. And well, this is basically a range proof. So we prove that the amount that we have, obviously we don't want to reveal it, the amount that we have lies in a certain range. And this can be done by doing proofs of integer addition. Next, the other example which combines the addition and multiplication is the auction, where we can have bidders, buyers, where we can place an order, let's say, of n items of m dollars each, and then we want to prove that we have more than n times m dollars in our bank account. And then, yeah, as I mentioned earlier, this example is a simple range proof where we want to prove that, let's say, we are over 18 years old. Okay, so now we turn to lattice-based zero-knowledge proofs. The equation here, or the statement here, is a pretty common one. Well, we are given the public matrix A and the vector U, and we want to prove the knowledge of a vector S, which has small coefficients, for example, 0, 1, or ternary, such that AS is equal to U. Okay, so firstly, there is the long line of research using the so-called Sturm proofs techniques. Well, yeah, they rely on quantum safe assumptions, but then they are not very appealing in practice because of the large proof size. And the main reason is that the soundness error is so big that the protocol has to be repeated many times. Then more recently, well, we have the other techniques which follow the Fiat-Shamir with abort paradigm, and basically, yeah, they also rely on quantum safe assumptions, but then the proof size is much smaller than for the Sturm proofs. And also the runtime is pretty fast because the protocols can be implemented using, well, algebraic structure of the underlying ring. So for example, number theoretic transform for polynomial multiplication and so on. So even though the proof size here is much smaller than the Sturm proofs, it is still linear in the number of commitments. This means that if we want to commit to like thousands or millions of vectors, then the proof size will blow. However, in certain applications, like in this talk, proofs of addition or multiplication, we don't commit to too many vectors. That's why the proof size we get are small, and then we'll see that in the last slide. Then on the other hand, we have a more generic approach, which is the PCP approach, like Aurora or Ligero. They rely on collision-resistant hash functions, and then the proof size is really sublinear. So it can be square root or logarithmic and so on. But then in terms of the runtime, it is much slower than using lattices. And this might be crucial in certain applications where we want to run the protocol multiple times and on the constrained devices like credit cards. So to prove, well, addition and multiplication, we lean on using the techniques on the left-hand side, kind of. So the starting point are the two papers, two very recent papers by Atema et al. And Esgines et al., where they provide a toolbox for proving certain relations between the committed messages. So what do we mean by that? So suppose we commit to some k messages, M1, M2, up to MK, and then we want to prove certain relations. Okay, so we split them into two. So first we have the linear relations. For example, you want to show that M1 plus M2 is equal to M3. Then all these types of relations can be captured by a matrix A and the vector U, and you would prove that AM is equal to U, where M is the concatenation of the messages and A and U are public. On the other hand, for the multiplicative relations, like proving that M1 times M2 is equal to M3, or proving that M1 has 0, 1 coefficients, where you would show that M1 times M1 is equal to M1. yeah, when I say times, I mean the component-wise multiplication. Then all these relations can be captured using public polynomials, f1, f2, up to, let's say, fv. And we would prove that fi evaluated at the messages m1, m2, up to mk is 0. And yeah, here I already mentioned, when we talk about polynomials, we mean with the usual vector addition and pointwise multiplication. So now going back to the statement I described before, then we can look at it in terms of the linear and multiplicative relations. We want to prove that AS is equal to U, which is a linear relation. And then I also mentioned that we want to prove that S has small coefficients, for example, binary, 0, 1. Then this would be the multiplicative relation. So just wanted to show the connection between these two slides. Okay, more formally, we can define the language. Okay, so for the specified linear relations and multiplicative relations, LP and PP, we define the language of the, this is a set of the messages, M, which satisfy the linear and multiplicative relations we want. So formally, AM is equal to U and Fi of M is equal to 0 for all I. So the first part of our paper focuses on combining the results from these two papers and constructing one big protocol where we send the lattice-based commitments to M1, M2 up to MK, and then we efficiently prove in zero knowledge that M1, M2 up to MK satisfy certain linear and multiplicative relations that we want. In other words, we show that M1, M2 up to MK belong to the language L of LP, PP. Okay, some people might ask, okay, so what's the connection between this and the title of this talk, where the integer addition and multiplication? Well, this is the second part of the paper, kind of. So the main strategy to prove, let's say, addition is that we start with the simple task. So prove that A plus B is equal to C. So what we're gonna do is that we will reduce this problem to proving that certain vectors, which depend on the integers A, B, and C, they satisfy linear and some linear and some multiplicative relations. So, for example, if we want to prove that A plus B is equal to C, we will binary decompose the integer A to be a vector here, the vector A. The vector A will be binary decomposition of the integer A, and then for the multiplicative relation, we have to prove that A has 0, 1 coefficients because it's a binary decomposition, and so on and so on. So this is kind of the more fun part of the paper, but unfortunately, due to time constraints, we don't really have much time to discuss that. Okay, as for the implementation, even for 128-bit integers, we obtain very small sizes. Like for addition, we have 25 kilobytes, and then multiplication is 40 kilobytes. And I think operations on 128-bit integers, well, this is enough in real life applications, but obviously we add like sizes for 512-bit integers. And then as for the runtime for 128-bit integers, the proving addition is around 1 millisecond and multiplication is less than 2.5 milliseconds. Then on the other hand, if we want to verify, then for both of them, the verification is pretty quick with less than half a millisecond. And yeah, and here in this link and also in the paper, we provide the code. So one can check that. Yeah, so thank you very much for listening.